Okay, welcome back. Hope everybody had a good spring break. What I got set up for today is this review, this study guide. And ignore the chapters there. It goes from the ones that we covered. That's just an old label. And then there's only 22 or something problems on here. So I figured I'd open up and go through a few of the worksheet problems. I picked up a little bit of a cold or something, and not that stuffy, but my throat's killing me. So occasionally I'll be stopping to use throat spray, and we'll see. Hopefully I don't lose my voice, but we'll go as long, as class time or until I lose my voice. Okay. Sorry, just moving it a little more. All right, this first one, as you can see, is just the MCAT equation already there in the answer key. Final temperature, so we're looking for one of the temperatures in the delta T, golden nugget. So it's gold, gives us the mass right there. Here's our first time, and then it tells us how much heat that it lost. And the thing that's missing then is the specific heat. And with that, we can find T. So it's really kind of a plug and chug where we take all the information given and put it in. Now, the units for specific heat of joules, the units given in energy were kilojoules, so you have to make that change first. And then I left it just as solving for X. You could have put T final minus T initial if you wanted. I solved it a touch different by just solving for the delta T first, and then going off where it started. Okay, then last is it loses the heat. So if the heat's being lost, then it's dropping in temperature. It'd be easy to put the same type of question, but say gives off the heat somehow. Two, what compounds are most attributed to depleting stratospheric ozone? Keep in mind this study guide and the worksheets as well were made for, for an in-person class that isn't open book, open note. So there will be, like the last test, there will be a couple problems that are pretty easy, but usually they'll be with some math or some conceptual thing, not one. This is just basically a memorization one from when exams were when they were in person. But A, B, and C, or A and B are the acid rain ones. VOC is volatile organic compound, and that's normal pollution, which is basically unburnt gasoline, either out the tailpipe of the car or at every gas station, a little bit of gas, a little bit of those organic compounds evaporate when you're putting gas in and taking the nozzle, in and out of the car. But it's really the CFCs that are the ones that destroy the ozone layer. Three, another example of one that's a touch too easy for our test. There might be one or two like this, but not 5 or 10. And a state function is that the path is independent. So an analogy that we used was elevation, right? It only matters the difference, kind of like the delta T above, right? It's just the initial and the final, but the difference between those two. And in chemical reactions, your initials, the reactants, and the finals, the products. 4, how much heat is absorbed by a copper penny? So this is another MCAT one. There'll be at least 2 MCATs on the question, probably just 2. And it'll change what you're looking for. This one both did the temperatures. So it gave us the mass there, gives you the specific heat. And then temperature rose from -8 to 37. So these are ones where if you put it in, change Celsius to Kelvin, you won't have a problem with this at all. If it's fine to leave it in Celsius as well, as long as you note the difference here is 45 degrees, right? So it changed from -8 to 0, and then 0 to 37, so a total of 45 degrees difference. If you just saw this and mistakenly put 29 degrees in there, you'll obviously get the problem. Since the Celsius and Kelvin are the same size, you can leave them in here because it's a delta T. It's just the difference between the two. So that's the trick with this one. Otherwise, it's a straightforward plug and chug. And again, the first one had that slight difference where it didn't give you the delta T. You had to find it, but otherwise, pretty simple. Three is just the concept of Hess's law. Once again, this was study guide was originally designed for an in-person class, and sometimes on the study guides I just put things in here to it's not a history test, but this is a pretty important concept, Hess's law, since it's what we did the whole chapter, right? It's not like the other chapters where there was some famous physicist last name associated with lots of different concepts. This was the only person talked about that whole chapter. And if most people have to take Chem 162, we'll do all this same treatment of products minus reactants again. So this name you'll see again and is dominant for an entire chapter. But it's just asking you about the principle and the concept of the path independence nature. It's not actually giving you a list of names to pick from. And it's pretty similar to up here above, right? That concept. All right, then 6 is using it. And so there'll be one of these on the test. This one, since there's 3 reactions, it looks like it might potentially be kind of tricky, but this one turned out to be pretty easy, where you just multiply all 3 by 1/2 and add them together. Again, you want to start off with things that are unique, and things that are unique catch my eye, like the Br2, the bromine here, right? You only have this on the product side in your overall, and then it's only in one of the 3 reactions, and the coefficient in front is a 1/2. So that tells you that you have to take this reaction and multiply it by 1/2. There's nothing else to do. Then the other thing that catches my eye is chlorine, Cl2 gas. The only place it is in all 3 reactions is on the reactant side. In your summary, you want it on the reactant side, which means you wouldn't flip that equation. And it wants a 1/2 here. And since up in reaction 1, it's a 1, that tells you, much like reaction 2, you're not flipping it, keeping it as is and multiplying by 1/2. Then everything from reaction 3 isn't in the overall reaction. So that means you just need to cancel it. And if you look above, say, reaction 3, reaction 2, the calcium hydroxide, the coefficients match. And since we're multiplying reaction 1 and 2 by 1/2, we must multiply reaction 3 by 1/2 as well. And that would cancel the water and also obviously the calcium oxide here. So this one looked a touch tricky at first, but once you find those chlorine and bromine and reactions 1 and 2 and see what manipulation you have to do, then it was kind of easy in just finding the right coefficient to multiply by reaction 3 to have everything cancel. Okay, 7 is really, part 2 of question 6, but some of these Hess's law ones of flipping the reactions can be kind of time consuming. So this is a way to make doing 6 properly basically give you 7 for free. So you can see that reactions 2 and 3 basically they nearly cancel each other. Then 1 is the biggest and it's negative. So even though you multiply them all by half, that same trend would continue, and it's definitely negative. And negative means exothermic. 7 is, really a coin flip problem on the test anyway. So this looks pretty similar to what you could expect on the test. 8, if the reaction is endothermic, what sign does it have? This is too simple for one of our exams, but the problem, 7 above, where you have to do some manipulation, and then even though it's a 50-50, if you've done the one above correctly, then that gets you the next one correct as well. So remember those energy diagrams. Endothermic means that the reactants are lower in energy, and you got to put the energy in to get them up to the product. And then vice versa for exothermic, the heat comes off. Number 9, we've got 21.8 grams of ethanol burned in a bomb calorimeter. So that's that device we looked at where it's basically an explosion contained in a metal cylinder. So no volume change means no work. Here's the temperature. It rose. Determine the heat capacity of the calorimeter. And then they gave you the molar mass. So you didn't, you don't need to, you shouldn't be spending time looking that up or calculating it on a test. All right, then this is sort of the opposite of the way it was presented in the book. So then they give us the reaction, that's the combustion reaction that's happening and the heat coming off. So first, let's figure out the temperature difference, right? They gave us our final and our initial, so the difference between those two. The reaction they gave us here, this is on a per mole basis of the ethanol. So they gave us 21 grams of the ethanol. That doesn't do us any good. We want to change that grams into moles. Using the equation they gave us, we can get rid of the moles, and we know how much heat should have been come off this specific amount of the ethanol. Then this is basically just the MCAT, where the C is the calorimeter. So we found the heat, and then the temperature change, isolate, solve for C, and we get about 15.7 kilojoules. And this looks like before, where, I'm not trying to trick you by rounding. There's not 15.6 and 15.8, something like that. The numbers are pretty, a ways off. Or by the number of sig figs, right? So you got 4 sig figs for the mass and the heat of the reaction, but just 3 sig figs for the grams and the temperature. So your answer should have the least number of sig figs. Again, definitions. This one's a little too easy for our test, kind of. A solute's best described as substance dissolved in some solvent, or solute is the thing that there's less of if they're freely mixed. And usually, if these are the general definitions, but when you go into lab, it's going to be some solid like sugar or salt thrown into water. I think we covered equations. This might have been from a chapter or a year when I didn't quite finish the last chapter, but we did before we went on to gases. So this would have been a problem for the last exam, not this current one. Same with 12. So you can kind of skip, 11 and 12. 13, we're back to heat, the thermodynamics. For reactions exothermic, do you consider the heat as one of the products of the reactants? Or on the reactant side, circle the answer. So another 50-50, but the delta H, if it's exothermic, the heat is a product, right? And we see that again in those energy diagrams. In an endothermic one, heat is a reactant. Without the heat, you'll never get to the products. 14, it's again the end of chapter 4, so that's another one that we already had on the last test. So you could skip 14. Or we will skip 14. According to the following reaction, how much energy is evolved during the reaction of 32.5 grams B2H6 and 72.5 grams of Cl2? Then it gives you the molar mass and the equation. So this is a combination of the last two chapters. This would be, it could be on the test, but this is sort of a tricky one. I don't want to say not fair, but and it's a longer problem for sure. I think these ones are, but this is basically making you do the limiting reagent from last time. So you've got these two amounts. We know how much energy comes off of the reaction. The question is which one of these do we have more of on a per mole basis? So what we have to do is like you did last chapter, where you take the gram amount and convert it to moles. So they did that first for what 32.5 was the B2H6, and then 72.5 grams was the chlorine. So it looks like there's less chlorine on a per mole basis. So that's the limiting reagent. We wouldn't ever get to 1.17, right? We would stop at 1.02. So we don't need to worry about this number here, because you would never achieve, you would never consume all of it anyway. All right, so once we know how many moles of chlorine, then keep in mind that there's 6 moles of chlorine for every, negative 1396 kilojoules. Okay. So put that here into the equation, and that tells us how much heat would come off, and then round it up. And again, no sig figs or rounding in attempt. And this one, it's tough to take a guess at these when you're doing too many math manipulations, unless you're really good. And there wasn't an E, none of the above here, and mimicking a test, so you could at least take a guess. If there's an E, none of the above, or a fill in the blank, obviously you have to solve the problem. 16, use the standard enthalpies to determine the heat of the reaction. So this is another Hess's law one, but we only have 2 equations. It's saying we want the reaction to look like this. That's our summary or total. It just showed me a little sign that says my internet is unstable. I don't know. It says it's connected. Okay, so what catches my eyes? We want the PCl5 on the product side in the summary. And the only place it is in either reaction is the reactant side in equation 1. So we need to flip that one, obviously. And then there's a 4 in front of it for our summary, and there's not what we're given. So this means we need to flip and multiply by 4. So 157 becomes negative, times 4 becomes minus 628. Okay, so then that would become 4 PCl and 4 chlorines. The 4 PCl is going to cancel perfectly with the 4 PCl3 here. The P4 matches up. It's on the right side. There's no coefficient difference in front of them. So once you know one thing that must be true for each of the reactions, you're set. And since we only have 2 reactions, we're done with that. So we leave that one alone and add the 2 together. And this one mimics what a fill in the blank type problem on the exam would be. "17 looks like is a gas, chapter 1. A gas sample weighing 3.78 grams occupies a volume of 2.28 liters at STP. So STP should set off a little alarm bell in your head that this is that critical thing we walked away with from that section on the chapter on gases, that 1 mole is 22.4 liters. This is our shortcut. Whenever you're at STP, this is true. What's the molar mass of the sample? So we know that it's 22.4 for 1 liter. And so if we have 2.28 liters, then we're really close to 1/10. But if we divide it, we see it's 0.1018. And then who knows how many digits continued. And that's how many moles there are. So we divide the total gram amount by this fraction, the molar amount, and we'll get the grams per 1 mole. And 3.78 divided by 0.1 should be about 37, and that's about where it shows up. If we look at the possible answers in here, if you go back to the periodic table, hydrogen is 2, helium is 4, then the next thing is nitrogen at 19. So answers A and B, they're possible, but they would have to be a mixture of hydrogen, helium, and then some other gas, right? Because the mass is too low. Then D, this could only be a no gas. Let me just pull up the periodic table. Right, so hydrogen is 1 times 2 because it's H2. Helium's 4. Then here's our other gases, the things that are in blue. It didn't say that you're at room temperature, but something close to it is most likely. So nitrogen would be 28, then oxygen's 32, fluorine, 1938. So the answer was 37. So it's got to be something, it's probably fluorine. If it didn't say that it's a pure sample, but then what was the other possible answer? 192 or something? That's above xenon. So maybe a mixture of these two. So 37 seemed like the most reasonable answer anyway. So a glitch in the system there. I don't know. We'll see how that looks on the video, but I don't know. It just shut things down and then came back on, and my microphone was muted for some reason. All right, it seems to be working again. Strange. Okay, we left off here. Right, A and B. So if you were guessing at this one, I mean, this one wasn't too hard, but once you like read it says, oh, molar mass, just looking at the periodic table. A and B aren't, and D don't seem the likeliest of answers. C seems like the most reasonable one. Of course, you have to do the math to find it for sure. Okay, 18. The total pressure exerted by a gas mixture. All right, this one clearly tells us we have a mixture. 1 gram of hydrogen, 8 grams of neon in a 2.8 liter container. It wants the total pressure. So, the ideal gas law, because we're not at STP, right? Our temperature is different. That's the critical thing. And we don't know the number of moles yet. With these, usually there's 1 or 2 ways to calculate this. You can find the total number of N and plug it in, or you could find the pressure of each individual gas, but it's kind of twice the math for no reason. So the tricky one with this, the neon's pretty straightforward because it's a monoatomic gas. It's the hydrogen. I guess my internet cut out, but then it keeps coming back and muting me and then opening back up. I don't know when it cut out. We didn't get that far that time. Okay, I'm unmuted now, right? Yeah, I don't know. Thanks, Nick, asking. Yeah, I don't know why it does that. It hasn't ever done this before. But it'll just drop everything, kind of reload, and then mute me like it started over. But it says it's still recording, so I don't know. We'll see how good or bad it looks afterwards when we just look at the recording. Anyway, so okay, back to this problem. You're combining the number of moles here, right? R is a gas constant. It's asking for the total pressure. So you bring it over and divide both sides by V to isolate P. And then sort of plug and chug. But the tricky thing is that remember that hydrogen gas is H2, not just hydrogen, the element. Excuse me. So this is basically the trick with this problem. Usually if you're on top of things and you would have missed, or you missed this problem, that's why, is because you forgot about hydrogen being H2 and not just hydrogen, the atom, like neon, the atomic, the noble gas, the monoatomic gas. All right, so with both of these added together, and they're near 1 mole, right? 0.89. Then it's just a plug and chug, and you can find the pressure. And again, round it off. This one was a fill in the blank one, and you can look on the last exam for those. I put the number of sig figs, etc., expected or desired. 19, what's the total pressure? So it starts off the same way, by gas mixture. So it looks kind of similar to the last one. 8 grams of methane, 8 grams of ethane in a 3.5 liter. All right, so pretty similar to the last one, kind of solving it different. And you could have done this in the last one too, right? P total is the individual pressures added together, sure, but then you're usually doing the ideal gas law twice. So like above, what's kind of nicer to do is just add a number of moles together. There isn't an N3 in either of these, right? It's just 2 gases, but the concept is the same. So again, it wanted P. So rearrange, plug and chug your things that are constant, or given. So the gas constant, the temperature. And then you need to grab the moles of each. So I didn't use a lot of digits here solving it. just 16, which it's really what 1601 or something, and same thing for the methane or ethane. Yeah, and that gets us our moles, and you add those two together. That's where the 0.766 comes from, right? So 0.5 plus 0.266, and then plug and chug. 20, the average speed at which methane molecule effuses at 28.5 degrees is 631 meters per second. The average speed at which an argon molecule diffuses at the same temperature should therefore be. What this comes from is that section there on the gas molecules effusing and diffusing, and how if they're at the same temperature, then they have the same overall kinetic energy. But since their masses are different, their speeds must be different. And the kinetic energy is equal to 1/2 mv squared. So same temp equals same kinetic energy. So you can set these two equal to each other. Then the 1/2 is going to fall out since it's on both sides. Then you just plug in the mass of each. So methane is 16, argon is 40. And it's the speed squared. They gave us the speed. And methane is lighter, and the argon is heavier. So we were looking for a speed that was lower. This one, you couldn't eliminate really any of the answers. You can see I'm not trying to trick you here, right? It's not 401 and 339 or something like that. And there was no E, none of the above. But you couldn't exclude any of these by the trend. So the lighter molecules moving faster, the heavy molecule should be moving slower, but all these numbers were below 631. So there wasn't really a way to rationalize or eliminate any of the other answers, A through D. '21 is a titration one, which we covered on the last exam. So we'll skip that one. There won't be one of those on there. This is talking about someplace in Tibet, telling us the elevation, the altimeter reading in the airplane. This is just, pressure. 48.26 centimeters of mercury, equal to what in atmospheres? This is a good example of a real easy one, where you're just doing a 1 unit conversion. I guess 2, right? But millimeters to centimeters is just moving a decimal point over. That's not much of a conversion. And then how many atmospheres? So this was a fill in the blank one, but if you've ever, done any scuba diving or been in a plane, your ears pop the pressure difference, and as you go up in elevation, you're expecting a number that's lower than 1 atmosphere. So if this was multiple choice, any number above 1 atmosphere is obviously going to be wrong, just in a logic and reasoning sense. And you can't have a negative number, etc. Of course, this one wasn't, multiple choice. It was a fill in the blank kind. All right, we stopped last chapter with the worksheets at 5, I believe. So we'll do a few here, see how far we get along. Probably all of them. They're kind of short. So 6, 7, and 8, maybe to 9. Forget if I opened up 9. The first one, this is a little too easy. But again, all these were designed originally when there was in-person classes. But it's good to, know the definitions here for pressure, although it's kind of obvious in the pounds per square inch, but a force exerted over an area. We're generally going to use atmospheres and millimeters of mercury. Those are the units in the gas constant that we saw and used, but you will on occasion have to change between units. Two, not on the test, but just throwing in some different, words that you want to get used to as a science major. A manometer is the small kind that's used in a chemistry lab. Barometer is the one that's for atmospheric pressure, like for weather stuff. A spectrophotometer is actually a real thing that's used for measuring light. I'm not sure C is even a real thing, and then E is just the two words thrown together. 3 looks like the same one off that study guide, so you can skip that one too. 4, a large balloon is initially filled to 25 liters. There's our temperature, 353 Kelvin. We're already in Kelvin, so we don't need to change it. At a pressure of 2,575 millimeters of mercury, what volume of gas will the balloon contain at 1.3 atmospheres and 253 K? So what this is it's taking PV equals nRT, the ideal gas law, and arranging it so that it equals the constant, so PV over NT. And then the number of moles didn't change, so you can drop the moles out. And it's a little harder to predict things when well, you have 3 variables changing versus just 1 and 2. So let's see here. And then also you have to convert these units one into the other. You can use atmospheres if you want by changing this, the 2575 to atmospheres, or you can change the atmospheres here to millimeters of mercury, either or. But we went from, we cooled down about 100 degrees, so a gas is moving slower at a lower temperature, but the pressure, 760, this is about 3 or 4 atmospheres. So the pressure went down, but the temperature also went down. Anyway, you plug these in and just solve for the unknown. Would we be able to you'd have to be really good at math to eliminate any of these. This is one where you just have to solve it. 5, what mass of NO2 is contained in a 13-liter tank at 4.85 atmospheres, 385? So there's no way to guess at this number. Too much math, I think, going on. But this is going to give you the info for the ideal gas law with just missing N, the number of moles. And then NO2 indirectly tells you what gas it is, and indirectly the molar mass. So you'd have to go either onto Google or grab your periodic table, and roughly oxygen 16. So 16 times 2 is 32, plus 14 is 46. And so it looks like it's about 2 moles because it's 86, so just under 2 moles. 6, using the graph below, determine the gas that has the lowest density. So this one is directly taken from any textbook, or it was in our PowerPoint here. And the concept here is the speed that they're moving and the average kinetic energy. So the kinetic energy is the peak, there is the average, but they're not all moving the same, right? The lowest density is going to be the one that's moving the fastest. So this is basically how a hot air balloon works. Right, and if you either the fastest gas or then the lightest gas had this type of profile. So I think if you go back in the book, like A is helium or hydrogen or something, and as you move along. So they're obviously not all the same, right? Otherwise their profiles would look the same. Uh, 7 here, let's see. The following reaction is used to generate hydrogen. 243 milliliters of gas is collected. So this would look like one of those collection ones we saw where you have, a tube going underwater, then some sort of enclosed container that the gas would bubble into. 243 mils of a gas collected at a total pressure, so roughly room temperature, but a little below it, or room atmospheric pressure, but a little sea level, a little below it. What's the mass of hydrogen that's produced? And then what this is saying, possible, useful. Possible means it is useful, table of water pressure, water vapor pressure. So we're at 25 degrees, which means you obviously want to use this one. It's saying the total pressure, implying that it's not all the hydrogen. So you want to take the 745 and subtract 23.78 to get the corrected value. And then once you have the corrected value, it's pretty easy, right? It wants the mass. So again, use the ideal gas law. You would take the volume into liters, change the temperature into Kelvin, the corrected pressure from subtracting 23.78 out, that would get you to the number of moles. And then last again is, you can't forget from previous chapters in the last exam that hydrogen, along with nitrogen and oxygen and all the halogens, come as X2. So again, another example where if you don't, you got to remember things from the past. But there wouldn't really be a way to guess at this. I mean, I would guess it's a small number because this isn't a big volume, and it's, basically it's near STP, but it's a little too much math to take an actual guess at it. 8, what pressure would a gas mixture in 10-liter tank exert if it was composed of, so we've got another mixture, here's our two gases, there's our temperature. So this is pretty much the same conceptually as the one on the study guide. You need to convert the gas value, the gram values of the gases into the number of moles. Then we've got temperature and volume, we've got N, so we're solving for P total. So you could get the individual P's or add up the number of moles together to give the total P. Nine's another one that's a bit too easy for our exam. It's just a definition. But we know while we're here, diffusion is that gas molecules spreading out in response to a concentration gradient. I wouldn't ask this on the test, right? Our key thing was to cover the ideal gas law and manipulations in general gas behavior, not these subtle details in the ways that, a gas company, or this is one of the ways nuclear energy is made by, they fluorinate uranium to make a gas called UF6. So anyway, a little beyond the scope, and just a definition. So for an open book test, it's a little too easy to just flip to that page and look it up. 10, simple conversion. This is a good example of a problem on the test that's meant to be quick and easy, where some of the other ones take a little longer. I probably wouldn't put the pounds per square inch on ours. It would probably be the millimeters of mercury to torr. But anyway, I think it's, what is it? It's 14.7 or something, or yeah, that would be 28. Yeah, 14.7. Just doing backwards math there. There's 14.7 pound, PSI is pounds per square inch. If you haven't heard of it or thought of it in a while, and again, it's more of an engineering term, but it's a simple math conversion. And so it's 14.7 per atmosphere. So you would just 2 times 14.7. So that's a pretty quick and easy one. So a good example of like a quick one on the test to make up for the ones that are a bit longer. 11, what pressure in atmospheres will 0.44 moles of Br2 exert in a 2.6 liter container? This is another ideal gas law one. You're given N, you're given V, and you're given T. The only trick with this one is just the usual converting T to Celsius to Kelvin, and then it's just plug and chug. Right? And there's really no way to guess at this. We're not at STP for you to take a guess. 12, so these worksheets come from a time when I used to teach the class with another instructor. So she put a lot of these problems in here where, like this one's the number of atoms. So you need Avogadro's number. In taking a guess at this, we're at STP, where 1 mole is 22.4 liters. 6.022 times 10 to the 23rd is 1 mole. So here we're at 10 to the 22nd and we're at 5. So this is about 1/10 of a mole ballpark. And this is close to 2, which is about 1/10 of 22.4 liters. So, this one's set up like a fill in the blank, but you would have to guess, or you would have to calculate it out. But if it was let's say it was like the problem above, when you're looking for an answer near 2, so let's say answer B was 1.9, it would be obvious without even picking up a calculator that the answer is going to be around the number 2. And A is too low, C, D, and E are too high. 13, going on here. How many grams of zinc metal are required to produce 4 liters of hydrogen at STP according to the chemical equation below? So this is one, you can't forget things. Chemistry is cumulative. At STP, 4 liters, so 22, that's about 1/5 of a mole. How many grams? So it produced 4 liters at STP, that's about 1/5 of a mole. It's in a 1-to-1. So then you'd look up the mass of zinc, and it's basically whatever, divided by 5, because it's about 1/5. The mass of zinc is 65. So 65 divided by about 5. It would be closer to like 13, 14, or 15 just by doing 1/5, but you'd be expecting a number somewhere around, 13, 14 grams. Again, it's a fill in the blank, so you'd have to pick up the calculator and work it out exactly, but this seems reasonable. Your answer should be in 3 sig figs. And again, the worksheets are a nice mix of fill in the blank and multiple choice. So, and you saw from the last exam, it was more multiple choice than it was fill in the blank. All right, that was 6. Open 7. I don't want to run out of time, and we already did a fair amount of these energy ones. Let me just skip up and take a look at 8. Yeah, 8, because there wasn't enough of this on that study guide. So there's a few energy ones here. Let's get to the light and stuff and the electromagnetic and the quantum stuff, just so we cover some of it. 5. Type of energy embodied in oscillating electric and magnetic field. So that's just reminding you, remember that the entire electromagnetic spectrum, every form of light, is this oscillating electric and magnetic field. Sunburns caused by overexposure to, I think everybody knows it's from UV, but this is just, a little too easy for our test, but it lists the different types of light possible. And then really it's asking you about the energy and then narrowing in on one of the types of radiation of electromagnetic radiation due to the damage that it can do to us. Oops, 7. When waves of equal amplitude from two sources are out of phase when they interact, it's called destructive. So this is the idea, right, of say jumping on a trampoline or something. And you know, when you've done this, it can be constructive, where two people jump at the same time and you transfer the energy and have a bigger effect. Same with light, or it can do the opposite. 8, there'll definitely be one of these where you go from the frequency to the wavelength or vice versa. Then, you know, if you double check this, since the full calculations aren't here, but the nanometers one is the only time we'll do this conversion here and use n nanometers, and which is 1 × 10⁹. So this one's going, and I don't have the, I mean, this one tells you it's a mercury lamp, and lamps give off light, and we talked about these a little bit. And so we're expecting a wavelength of light, sort of in the visible range. I mean, you can see these lamps, so, they're a little bit higher energy usually. So 700 or 800 nanometers was on the high end, and 400 or something was on the lower end. And these things, I mean, you may not know that unless you're around them, but it's in the right range. 9 blank. Some kind of something are used to destroy molecules within unwanted cells, cancer, radiation. Okay, so a sunburn just does the surface of your skin. A and B have to do with actual radiation. It's kind of beta and alpha aren't really fair questions. Microwave and infrared does nothing. That's just night vision goggles. Visible light doesn't do anything. Doesn't destroy unwanted cells, right? So X-rays, if you ever had, I assume everyone's had an X-ray at some point. They put that lead blanket on you. And gamma rays are higher energy. So this one's indirectly asking you to rank the energies of and some cutoff point, right? So this is above a sunburn, and the only two types of rays that are above the sun, that intensity, that energy, are X-rays and gamma rays. Calculate the energy of orange light emitted per photon by a neon sign. It doesn't really, the orange light doesn't really mean much to you unless you know the frequencies that well. This has to do with the HV. So really, they gave you the V. So you're really just multiplying this times Planck's constant to get the joules. It's only one multiplication, only one math function. So that's a pretty good example of a quick and easy one mathematically. Calculate the frequency of green light emitted by a hydrogen atom, a wavelength of 486.1 nanometers. So this is just the opposite of the problem above. I'm not sure, did she leave? Okay, I used to have all the equations up here. Her name was Kayla. She must have cut them off. So this is, right, C is the speed of light equals wavelength lambda times nu, which is the frequency. And so this is the opposite of the problem above, where you found the nanometers. Here they're giving you the nanometers, right? So you want to get out of nanometers and into meters, and then the speed of light is 3 × 10⁸ meters per second. And I don't know the frequencies offhand, and it seems like several on this worksheet are fill in the blank, even though the next one isn't. What total energy is contained in 1 mole of photons, all with a frequency of 2.7? So this uses the same principle as above. Up here, number 10, this is calculating just 1 photon, and then you would multiply it by Avogadro's number. Kayla, who I used to teach the class with, liked to mix in previous chapters a bit more, which you've seen, where you have to remember, hydrogen is H2 or Avogadro's number, something like that, like here. I tend not to do that as much and try to kind of compartmentalize the chapters, but chemistry is a cumulative subject or topic. Calculate the wavelength. 13, calculate the wavelength. This is one using the mass, which I'm not going to put one of these on a test. So this one's overkill. This is a little too physics heavy for us. I think you'll get this in a physics class. And it doesn't, these ones don't really prep anybody for OChem. The speed of these subatomic particles, especially electrons. So I would skip 13. There won't be something like that on the exam. 14, I don't know if I would ask it like this at n equals 3, but maybe list, like even listing, this is a little too easy for an in-person class, but for an open book class, but decent for an in-person one. N equals 3 is telling you that there's 3 possible types of orbitals, right? There's only 4 completely possible S, P, D, and F. And this is just if you are in the third row of the periodic table and go across how many orbitals are there. Different types of orbitals, what that meant. So that was what? That was 8. Or that was 7. That was 8. Do I have 9 open? Yeah. Okay, 9. Which of the following quantum numbers describes the size and energy of an orbital? This is, again, another definition one, and I'm not too big on making you memorize the names of the individual orbitals. So this one is not really a fair representation of what would be on the exam. But 2, determine the energy change associated with the transition from N to 2. This is just plug and chug straight from that formula of the hydrogen atom, where you have, it's the N squared. So 2 squared over 5 squared times that constant. You subtract those 2, get the difference. That's a pretty plug and chug one, which I know it's not, the full solution isn't here, but so the worksheets are a little bit better for you to go and look back at the slides or your notes and then see if you can solve it and have the answer there. And if you can't, then you can run through the video where I at least explain it a little bit better in detail than just a number. 3 is a decent example. This is kind of easy to look up, but it'd be a good, and 4 as well is just a quick check mark. Even if you're flipping through the notes and you don't know it, it's still an easier problem. Identify the orbital. Now it's a little tough. That's why there's a second drawing over here, but you can see that it's 2 lobes, which means it's a P, and it's trying to show you that, this one is Z, X is in the plane of the board, and the Y is coming out at you and going away from you. And the focus of the, distribution map of the electrons is on the X, so that would be the PX. 4 is a little tough to tell exactly where these lobes are at. Distinguishing between the different types of D, and that's why I just left it as a D, not specifying which one. D, X, and Y. Yeah, I would say at least it has Z character to it, right? These seem to be sticking up, not in the plane of X and Y. So it's got to be probably DZY. But anyway, generically, what you'd see on the test is like a P orbital, a D orbital, an S, or an F. And it's, 4 lobes is clearly a D. 5, electromagnetic spectrum, visible lights immediately between 2 other wavelengths, name them. A little bit too easy for our tests, but maybe for a quick one where you could just flip through your notes, or, this is really just looking it up. Again, the worksheets were from an in-person class originally, but still several of them are good. Invisible, you know, night vision glasses use the next highest energy when it's, when it's dark out. So infrared, and then UV is what's just above visible, and why we put on sunscreen. Which of the following transitions, in general, but it's still true where focus is a hydrogen atom, represent emission of the longest wavelength photon? So I like this question because it's really easy if you know the idea of the model and what emission means. And then longest wavelength. So the longer the wavelength, the shorter the frequency, right? And so the photon is the energy of light. Emission means it's coming off. So 1 to 3 would be going up. That would be absorption. We're looking for going down. Right. The longest wavelength, think of the different wavelengths that we saw on the spectrum. What was it? Radio waves, microwaves, then radio waves. So that would be they're the weakest energy-wise. Then it's an n squared thing. So A doesn't make any sense because it's going up. Right, then 3 to 2, okay, 3 to 4, C doesn't make any sense, it's going up. So answer B could be it, D could be it, or E could be it. What's the difference between them? As you do the n squared factor, the distance between them got smaller and smaller. So that means the energy associated with the transitions, as the n value got higher, the distance between them got smaller. So 3 to 2, 5 to 2 would be the shortest wavelength, the highest energy, the biggest gap. And 3 to 2 would be in between. And then 5 to 4 would be the most accurate. For this one, just skip to the PowerPoint and pull that up. Pull up a picture of it, ads opening slow. No, I don't want to start my free trial. Got it. Go away. So this is the picture I was looking for. So I was asking, emission means the electron dropped down and you saw light come off. So any of the ones going up didn't work. I think that was A and C. So then what's the smallest gap here? It was 5 to 4 versus say 5 to 3 or 3 to 2, right? Which would, 5 to 4 isn't even on here, but it would be this, an arrow from here to there. And this isn't drawn to scale. So if we go back up, remember the equations, this was the equation where it's 1 over n squared. So it looks more like this is drawn a little more to scale. And 5 isn't even on here, but 5 would be, somewhere in here, really close to 4. Where was that? That was this one, number 6. So this was a good problem in the sense of you don't need a calculator, but you have to understand what each one of these things means, right? That it's emission. So A and C are eliminated right away. Then the longer the wavelength, the weaker the frequency. The longer the wavelength, the frequency goes, they're inversely related, and so you're going to get hit with less of them because they're so much longer, which means they're less damaging. So we're looking for the weaker one. All right, hope that made sense. Sorry. 7. This one you could just look up, and it's a little more, just the quantum numbers. I'm like, these are important for chem majors. The thing is, you won't use these in OChem. So I tend not to like these questions that focus in on them too much. I don't think they're on the MCATs or anything. They're really only important for chem majors in the future. And the numbers were just meant to introduce and validate the shapes of the orbitals, which we'll use in the coming chapters. But anyway, the possible values for N and ML for an electron in a 4D. So 4 N equals 4, right? Because you don't have d orbitals before that, and it's telling you 4 right there. So that one's sort of redundant. Then the M sub L is that second number where right here it's just showing you all the possible ones. And 8's more the same. So for an F orbital, right, it's giving you just all the possible ones. Because F doesn't happen until N equals 4 in the table, and then the M sub L is 1 minus, that gets you to 3, and then it's plus or minus included 0. So 7 and 8, I don't, and 9 here, I don't really care for these as much. I won't be putting one of those on the test, because you could just flip through your notes and look it up anyway. And after this chapter, we won't use the quantum numbers again. We will use the shapes of the orbitals, and the number of electrons will be important. So for our test, I'm not going to put 7 through 9. I'm not going to put one of those on there. But there will be these diagrams and the orbital and the electron count, because that's what you'll use in coming chapters to understand bonding, and you'll use in OChem as well. Since it's open book, there won't be one of these, right? But notice how like this chapter is a real physics heavy chapter. Like none of these, I know no one knows it, but all of these guys, Pauli, Hans, Afab, and Heisenberg, are all famous physicists. And they're not really thought of as chemists, even though they discovered the things that are the basis for the way chemicals bond. All right, but an 11 is a good example. So orbital diagram that represents ground state of nitrogen. So sure, sorry. Trying to get to the periodic table. Where's nitrogen in the periodic table? Right, there's 1s, there's 2s. You come over into 2p, and it's the third element in the p block. So we come back. We come back over here. 1s is filled, 2s is filled, and then we want 3 electrons in the 2b. So answer C and D are clearly wrong. E as well. What's the difference between A and B? That's our up here, same quantum numbers, Pauli exclusion, and then electrons are negatively charged and repel each other. So they're not going to pair up. When you have a degenerate orbital and equal energy, then you can push it out and put 3 separate. And we'll cover this again after the exam, the uniqueness and usefulness of unpaired electrons. The element that corresponds with this configuration, so all these are filled as we march along. We're looking for 4s1 3d6. You can add those two together, and this means the 6th element that's in that the fourth row of the periodic table. So if we go to the periodic table and sixth element over, that would be 1, 2, 3, 4, 5, 6 right here, chromium. So that's from the electron configuration to the element. 13 is doing the opposite. So you'd go to the periodic table, find selenium. It's right below sulfur, which is right below oxygen. So it's got to have the P4, which would eliminate answers C and D. So then what's the difference between these? You need to make sure you're in the right row. So argon is the core, and then you would just move across. So if we go back to the periodic table, it wants to know about selenium, which is here. Let me just push the, right, so 4, there's S block, so 4s2, 3d10, then 1, 2, 3, 4 in the P block of the fourth row. So we'd be looking for argon is the core, and then the outermost or valence electrons. So there's 4s2 moving along the 3d10, then into the P block. We're still in the fourth, and 4 electrons there. So 12 and 13 are pretty much the exact same, just opposite to one another of solving it. And it looks like 14 is same conceptually as 12. Find magnesium and then move across. It didn't have the core in here, did the full, but there's your core is 3p6. But let's go find manganese. It's right here, the 25th element. So again, it'd be argon as the core, but that one didn't have argon, the core in there, but still 1s2, 2s2, 2p6, 3s2 moving across. Our valence ones are just S and P, but we've got 1, 2, 3, 4, 5, 6, 7 electrons in the combination of 4s and 3d. Okay, I made it all the way through. That gets us to 145 and finished. We skipped that one, but we got at least did some of the worksheet from 9. I don't know if I didn't pull up worksheet 10 just while we're here, so I can tell you whether 10 is worth looking at. Yeah, 10 is okay. Yeah, 10 would be worth looking at as well. Look, it's got some of these. We didn't get to ionization energies or electron affinity. So only half of worksheet 10. Oh, whoops, it didn't share it. Hold on. So only the first 5 problems, 6 there are good for worksheet 10. The 7, 8, and 9 were the end part of the chapter. We didn't get to these trends of the size of the elements. Okay, yeah, we're out of time. I hit the unmute button if you want to unmute and chat about anything. The worksheets, everything in that study guide there on Lima. I'm around if you got extra questions or anything. You can send them by email, and then the test is going to be on Lima just like it was before. So a good way to kind of study or prep, you know, format wise, is go back and take a look at the old exam versus the study guide, and also the problems embedded in the PowerPoint. Those are really good to go over as well, because they show you how to solve it step by step. Versus the study guide that has it, but it's not necessarily animation step by step wise.
When was the test again?
This week, Wednesday, our next class.
All right. Hey, double checking.
Yeah, no worries. So yeah, questions, comments, thoughts, feelings.
I have a question. When you email the test, the paper version of the test,
Yeah,
how does that come through La Lima or?
I mean, I email it through La Lima, but you'll get it directly to your email.
Okay, I was just wondering because last time I didn't get one.
I can,
Which is
I'll
fine.
also, I can attach it to the test on La Lima, so it'll be in there somewhere. But sometimes, like when you have when you're looking at a web page and you're like focused or something, like searching around for one little icon that downloads the test is a little annoying versus an email that's like directly sent to you and it's attached to it. But I'll do both just in case.
Okay, yeah, I figure. I mean, the test once you open it, right, it starts timing. So I mean, I
Yeah.
probably won't, but just in case, I noticed some of the questions might have been easier to look at on a different version of the test.
Yeah, it's La Lima, and then I can't change the formatting and the way La Lima presents it. So, but I agree with you. It's nicer to I like having an actual piece of paper to look at too. So, and you can
Mhm.
print it out and kind of work on it. I don't know. I like yeah, I guess it's just sort of what you're used to. I guess I'm not as electronic sort of as everyone.
Yeah, me either.
Yeah, so on there he just asked about the chapters 5, 6, 7, and then yeah, that half little bit of 8, because 7 and 8 are really one big chapter, but we didn't get to the end part of 8 on there. Cool.
Professor, I just have a quick question.
Sure.
So I just want to confirm the time the of our exam on Wednesday. So that's gonna be 12:30.
Yeah, I'll start at 5 minutes late and it'll go for an hour. So we'll start technically at 12:35, just like last time, and it'll go to 1:35.
1:35. Okay, yeah.
That
Thank
way,
you.
yeah, that way everyone's got a couple minutes to, not to be rushed, and then 10 minutes afterwards for whatever.
Mhm. Yeah, makes sense. Okay, thank you.
All right. See you
See you on
then.
Wednesday. Yeah, thank you. Bye-bye.
Bye.